Soil is home to over a quarter of all living species, anchoring all life on Earth, yet soil biodiversity is threatened. Good day, my dear panelists. We are CM Group 3 and our study is about spatial estimation of soil erosion in the Alviera sub-catchment in Porac, Pampanga using RUSLE model and GIS techniques. As the SDG Research Center puts it, half of the topsoil on the planet has been lost in the last 150 years, at an alarming rate of 26.4 billion tons of soil loss per year, a rate that is 10 times quicker than the soil replenishment. Soil erosion occurs when soil particles physically separate from a land surface. It contributes significantly to land degradation. Also, the effects of soil erosion go beyond the loss of fertile land. Agriculture and food security are also threatened. Soil erosion also results in increased flooding, silt pollution, and other serious issues. The loss of the topsoil has become a significant environmental threat. Also, it is aggravated by several factors, including topographical factor, precipitation, soil properties, unsustainable land use, and land cover patterns, as mentioned by Ganasri and Ramesh in 2016. Additionally, due to the Philippines' steep topography, depressed uplands, and severe rainfall events, the country is highly prone to soil erosion. Unfortunately, it was discovered that the erosion database of the country is also outdated, with a rate of 106.82 tons per year in Region 3 in 1993. This data gap may reflect the lack of attention to soil erosion management and assessment in the country. Furthermore, rainfall or rainwater runoff is a predominant contributor to soil loss. Every year, around 20 storms hit the Philippine area of responsibility, accounting for 25% of global cyclones. Also, Porac has the highest relative humidity, averaging 84% from July through September. Figure 2 shows that August is the wettest month in Porac, with rain falling for 27.8 days and regularly accumulating up to 380 millimeters of precipitation. Heavy rains can cause extensive surface runoff during the season, causing soil erosion. And given the topographical map of Porac, Pampanga, where the study area is located as shown in Figure 3, it shows that majority of its plains have a hilly to mountainous topography. Due to its slope, it can perpetuate the process of rainwater or runoff saturation in the area. Banjari and others in 2021 also highlighted that increased soil loss rates are situated in mountainous watersheds. Alviera is a mixed-use land development covering an area of 1,800 hectares. The maximum elevation of the area is estimated at 68 to 198 meters above sea level. The changes in land use and land cover in the areas within the Alviera may also have a substantial impact on vegetation cover and runoff speed, resulting in an increase in soil loss in the concerned sub-catchment. However, despite the existing problem of soil erosion in the Alviera as shown in Figure 4, there is a data gap in terms of soil erosion hazard map in the area, as the modern soil loss estimation remains to be a challenging problem in the Philippines. As a result, this gap must be addressed. This study will concentrate on the entire boundary of Alviera. Wherefore, this study will attempt to determine the intensity of soil erosion risk in the subcatchment.
With that, the general objective of the research project is to assess the soil erosion risk in the Alviera subcatchment using RUSLE model and GIS techniques. And the specific objectives of the study are to gather and collectively analyze the spatial variation of underlying individual key factors responsible for generating soil erosion in the area. Second is to estimate the annual soil erosion rate in the Alviera subcatchment, and lastly, to produce a refined map of soil erosion risk by demonstrating the performance of GIS and RUSLE in estimating soil loss. The research aims to establish a risk assessment of soil erosion in Alviera, raise awareness about the degradation of our soil biodiversity, and assist in advocating for sustainable soil resource management for a food-secure future under SDG 2 Zero Hunger and SDG 15 Life on Land. The study also aims to close data gap regarding soil erosion hazard maps in Alviera and practice gap related to the lack of studies combining RUSLE and GIS techniques for predicting soil erosion in any case location within Central Luzon. Moreover, the study may help to highlight the region's lack of urgency in enacting soil mitigation measures. And finally, the outcome of the study is considered significant for the following stakeholders. First is the Alviera land users and planners. The study will help land planners, especially Ayala Land, Leonia Land, and the Land Management Bureau, demonstrate the pervasiveness of soil erosion in the sub-catchment and aid them towards sustainable soil erosion control and land resource conservation methods. Second, government leaders and policymakers. The study may also assist, especially LGO of Porac, in offering scientific advice that may help formulate and implement comprehensive and effective soil conservation policies to support long-term sustainable growth and alleviate the effects of soil erosion in the given location. Third, future researchers. The study's findings may be a valuable source of knowledge for future scholars interested in conducting related research in the area. The study may also act as a reference for future advancements in calculating soil erosion across the country. And lastly, Disaster Risk Reduction and Management Council. The study's findings and outputs will help produce a soil erosion hazard map that will extremely help in identifying areas at risk of substantial soil loss and serve as a baseline for future risk management strategies for the area. Furthermore, past scholars have also developed many soil loss models for undertaking systematic assessments and examinations of soil loss in an area. To properly show the suitability of the revised Universal Soil Loss Model for spatial estimation of soil erosion in the Alviera subcatchment, the following models for estimating soil erosion are listed, and their limitations are described. These models have various limitations and may not suit some applications and conditions. The current state of certain models is not suitable for use and must be modified first. Others can only simulate small areas and are ineffective due to factors such as time-consuming and costly, while others do not take into account parameters such as runoff, which fluctuates with runoff and sediment content. Based on the analysis conveyed from the different case studies, it can be concluded that the RUSLE model is the most efficient soil loss estimation model. Numerous applications of this method in different countries resulted in excellent outcomes. Moreover, the RUSLE model produces a more accurate estimation and model outputs. Additionally, it also reveals the practice and research gap in terms of similar case studies in the Philippines. It is critical to emphasize that the empirical soil loss model has not yet been broadly implemented throughout the country. Thus, this significant analysis highlights the critical need for more research focus on applying advanced and efficient modern techniques for assessing soil erosion risk in various locations around the Philippines, especially in Central Luzon.
In addition to that, Table 1 shows the summary of the calculating models that will be used in the study to solve the different RUSLE factors, such as rainfall erosivity, which will be derived from the model of Josue in 1989. Second, the slope length and the slope steepness will be measured based from the computation model of Moore and Birch on 1986. Then, the soil erodibility, land management, and conservation practice factor will be generated from the value determined from the study of David on 1988. Then the gathered values will be incorporated into the equation of RUSLE model of Renard et al. On 1997 to predict the annual rate of soil erosion. The figure illustrates that the soil erosion is a serious environmental issue, particularly in places affected by natural forces and other anthropogenic influences like the Alviera sub-catchment. However, estimating soil loss is a challenging research problem in the Philippines due to the lack of studies using RUSLE and GIS to assess soil erosion risk, which also results in a lack of soil erosion estimation study in Alviera. RUSLE has been used successfully in several countries. Furthermore, the study will consider all of the required parameters in RUSLE. The model inputs and files will clip to GIS environment to build each parameter raster layer. The raster calculator tool will merge all of the raster layers using the RUSLE equation to compute the soil erosion rate and generate a single file of soil erosion risk map indicating the soil loss rates within the boundary of the area. With that, this will allow the assessment of the risk of soil erosion in the said sub-catchment. The methodology followed in this study is shown in Figure 7.
Analytical research will be used in the study. The RUSLE model will be used to estimate soil erosion quantitatively. Historical and simulation data will be obtained using satellite and ancillary data based on rainfall events, DEM, soil types, RS images, and literature reports. GIS will then be used to process the input files to aid the soil erosion risk mapping. This will be divided into 4 major sections: collecting geospatial data for RUSLE factors, processing the geospatial data for each RUSLE factor, calculating soil erosion rates and risk mapping, risk assessment and analysis of key influencing factors of soil erosion. The geoportal will be used to extract data on land cover and soil classification map of the study region in Alviera, Pampanga. Then it will be used as data for C and K factors respectively. WorldClim is the website that will be used to obtain raster file for the mean monthly precipitation in the study area to derive the R factor. Elevation data that incorporates slope length and steepness will be acquired using the DEM for LS factor. Conservation practice data for P factor will be gathered based on literature reports present. However, if there will be absence of any recorded data on the conservation practices of the sub-catchment, the values that will be assigned for the P factor will be based on the C and P factor ranging from 0 to 1, with 0 having good management practice and 1 having poor management practice. Then GIS will be used to process the gathered spatial information by entering data and then layering it to form raster layers. After creating a map for each parameter, the average annual soil loss will be calculated by multiplying all the raster layers of the factors in the GIS raster calculator using the RUSLE equation to obtain a single raster file displaying the rates of soil erosion within the Alviera, Pampanga as shown in Figure 8. In determining the region covered by each erosion risk class, the raster soil erosion rates will be converted into one vector layer. Soil erosion rates will be classified into risk classes ranging from insignificant to catastrophic as displayed in Table 2. Then regions belonging to the same risk class will be combined. Their area in square kilometers will be calculated using GIS field calculator function, which will calculate the polygon areas for each soil erosion class as shown in Figure 9. In conclusion, the mean soil erosion rate will determine the soil erosion rate for the Alviera sub-catchment.
This is the research project's timeline. Some tasks are independent whereas others can be accomplished concurrently. For example, if the K factor is already obtained, it can be preprocessed without waiting for the other RUSLE factors to be acquired. The data collection will be completed within the first month. Field investigation may be conducted to validate and accurately assess the data collected. From mid-March to late May, various tasks such as preprocessing, such as restoration, reprojection, clipping, and actual processing will be carried out. Finally, in June, risk mapping, calculation, analysis, and evaluation will be completed. To summarize the project, it is expected to take up to 4 months to complete. Lastly, this is the summary of the reference to use in today's discussion.